All right, Math 136 students, this is the second part of the final exam review. So we're going to be looking at the material that's listed as Day 2 material and working through these examples. So this first one says solve using the quadratic equation or formula. Give an exact answer. That means no decimals for rounding of any kind. So the problem is that when you want to do the quadratic formula, you need to remember your formula. First of all, it's x equals negative b plus or minus square root b squared minus 4ac all over 2a. Now, if you don't know what a, b, and c are, then that doesn't really help. A, b, and c are the coefficients of this trinomial. A is always in front of x squared, b is in front of x, and c is in front of c is the constant when you are set equal to 0. Now, the problem is this is a fractional kind of thing, so if you want to get rid of the fractions and not have to deal with that when plugging into the quadratic formula, since this is an equation, we can multiply both sides by the LCD of this denominator set, which is 2 and 5, or the LCD would be 10. So if we multiply that, that gives me 5x squared. This would be 30 divided by 5, so that's going to be plus 6x minus 30, because you do still have to distribute the 10 to the 3, and equal to 0. So now this is my a, this is my b, and this is my c. So x equals negative b would be negative 6 plus or minus the square root. Then we have 6 squared minus 4 times the a, which is 5, times the c, which is negative 30, all over 2a. So we're going to work out that inside. This is going to equal negative 6 plus or minus the square root of 36. This is a negative times a negative. In fact, this is negative 20 times negative 30. So since they're both negative, it's going to be positive. It's going to be positive 600. All divided by 10. So x equals negative 6 plus or minus the square root of 636 divided by 10. Now, obviously, 636 is definitely got a possibility for perfect squares possibly being underneath it. If we try 36, that doesn't work because it doesn't go evenly. What about 4? 4 and 159. Let's try 16 just to make sure. 16 does not work. 159, I believe, is a prime number, but I'm just going to double check that. Nope, 3 goes into it. But 53 is prime. So it's going to be 4 is the only perfect square that goes into this. So we're going to pull this out as a 4 times, and it's 636 divided by 4 was 159. So this is going to be negative 6 plus or minus the square root of 4 is 2 on the square root of 159 all over 10. So in reduced format, we can reduce all the outside numbers by 2. So that is negative 3 plus or minus the square root of 159 over 5. So there is our exact answer, and there are 2 solutions because it is plus or minus. For number 2, we're trying to write the following expression in a plus bi form. Remember, we rationalize these because I is really a radical in disguise. So our first step is to use the conjugate and multiply the numerator and denominator both by the conjugate of the denominator. We'll FOIL this out. So this is 14 minus 28i minus 6i. Be careful with your signs on this next part. This is a positive 12 when we multiply I squared. So that's going to end up being a negative 12 overall because of that I squared being a negative 1. On the bottom, we get a 4 minus an 8i plus an 8i, so those cancel. And then we get negative 16i squared, which is really a positive 16. So this becomes 14 minus 12, which is 2. I've got negative 28 minus 6 more, so that's going to be a negative 34i, all over 4 plus 16, which is 20. But because we want a plus bi format, we're going to split this into 2 separate fractions, and we're going to reduce them individually. So this is 1/10 minus 17 over 10i, because everything is divisible by 2. Okay, moving on to number 3, we're trying to solve this absolute value equation. You need to isolate the absolute value first. So we'll subtract over the 14, that makes that 15. We'll divide both sides by 3 so we can get our absolute value by itself. And this says that no matter we're trying to find x's that when we put them inside here, the absolute value of this will equal a positive 5. So there's two possible ways that this could equal an absolute value of 5. That's if the inside is equal to a negative 5, because absolute value of negative 5 would be 5, or the inside could be equal to a positive 5, and that would still be an absolute value of 5. So if we add 1 and divide by 2, we get a negative 2 for one solution. If we add 1 and divide by 2 over here, we get a 3. So there are two separate solutions that both would work. For number 4, we're trying to solve a radical equation. So same idea, we want to make sure that we isolate the radical first by adding over the 4. And to get rid of a square root, we will square both sides. Now on the left side, that just leaves you with x plus 10. But on the right side, it is you have to square the binomial, which means write it twice and FOIL. This would be x squared plus 4x plus 4x plus 16. So this is x plus 10 equals x squared plus 8x plus 16. Get everything on one side by subtracting the x and the 10 over. So this is a 7x and a 6. That factors into x plus 6 and x plus 1. So I have two possible solutions, which is negative 6 and negative 1. But remember, radicals have a domain issue. So it's not possible always that both of these could come out to work nicely, because when we take a square root of a number and then minus the 4, we don't know if this is going to end up being the same answer as over here. And that has to do with the fact that we squared this. We don't know if this was a negative or a positive, and when you square it, you've made it all positive. It doesn't always have to be a domain issue, but it's not going to always work that every solution you get will be one that works. So anytime it's a radical equation, we're just going to make sure we always check our solutions. And this equals negative 6. So this would be square root of 4 minus 4 equals negative 6. That's a 2 minus 4, which does not equal negative 6. So that is not equal, so negative 6 does not work. If we do the square root of negative 1 plus 10 minus 4 equals negative 1, this is square root of 9 minus 4 equals negative 1. That's a 3 minus 4, which does equal negative 1. So you have to check your solutions on radical equations. All right, for number 5, we're supposed to solve the following inequality and express our answer in interval notation. So when you have a compound inequality like this, that means there's two different inequality symbols. We want to solve this by getting x by itself in the middle. So you can do that as long as you treat all three parts the same. So I'm going to multiply all three sides, which is the left, the center, and the right, by an 8. That makes this negative 32 less than the 8 in the middle would cancel. So I just have 3x plus 1 less than or equal to negative 16. I would then subtract 1 from all three sides. That makes this negative 33 less than 3x less than or equal to negative 17. Divide all three sides by 3. That makes this a negative 11 less than x less than or equal to negative 17 over 3. We're supposed to express our answer in interval notation, so our x can go between negative 11, but not included, up to negative 17 over 3. And that is included, so it has the equal to sign, so we're going to put a bracket. Now for number 6, it says solve the following inequality and express your answer in interval notation. Okay, again, anytime there's absolute values or radicals involved, we usually try to isolate that piece first. So I'm going to subtract that 3 over. Now with absolute values, they're always positive, so being greater than or equal to 3, we have to think about how could that happen. And then for if you're doing less than or equal or less than 3, how would that happen? So if you want, and the way you think about how does it happen is you ask the question, what is an absolute value really measuring? And it's a distance. So if you want your distance away from something to be greater than 3, that could be that you have a number, say in the middle. Let's just kind of think about a number line. Whatever this is, you want to be a distance of 3 or more away. So let's say we're 3 and minus 3. We want to be here. We want to be beyond this and beyond this. That means our distance away from our center is greater than or equal to 3. So if you think about it visually like this, you can help yourself when setting up the problem. So the first part is you set the x minus 7, which is the inside, less than or equal to negative 3. This gets us to the minus 3 case where we went 3 to the left of our number and we're staying further away. So we're headed towards negative infinity. And then the other case, which is an OR, because greater than is an OR problem, is that you have your inside or your argument and you actually go to the right, which is you're saying greater than or equal to 3. So when we solve these, you get that we add 7 here, and this would be 4. And we would add 7 here, and this is 10. So just to think about this, imagine that, because this is centered at 7 technically, because it's x minus 7. And it's not always easy to do each of these graphically, especially if you have like a 2x involved, but this is an easy one to show you that this really does work. If I go 3 to the right, that's a 10. If I go 3 to the left, that's a 4. And if I want my distance to be greater than or equal to 3, I need to be going away from my 7, because my distance should be bigger than 3 or equal to 3 from 7. So then in interval notation, this would be negative infinity to 4 with a bracket, union with bracket 10 to infinity. So that is our absolute value inequality. If this had been a less than, we would have wanted to stay within 3. So we would have set it up as the x minus 7 is between a negative 3 and 3. You set up an and case then. Okay, for number 7, we are trying to solve this inequality that is, it's bigger than an x to the first power. So we usually use a sign chart to help us figure these out, and we need to try to factor first. So I can pull an x squared out of the first pair, and that would be 3x minus 2 using factor by grouping. I can pull a minus 9 out of the second group. That would also be 3x minus 2, less than 0. So this is 3x minus 2 and an x squared minus 9, since we have the common binomial. And then we can also factor this again into an x plus 3 and an x minus 3. Now, a lot of people try to set each of those less than 0 and just solve it. That's not true, because the sign of the left side depends on all 3 factors multiplying to something either positive or negative. We want it to be something negative since we want it to be less than 0. So the only way to really do this efficiently is to make a sign chart by finding all of these values that make them equal 0, and we will put them on a number line from least to greatest. So that is negative 3, 2/3 is the next biggest, and then positive 3. We write down our interval notation. These will all be open circles or parentheses, however you want to think of that. So this is negative infinity to negative 3 parentheses, negative 3 to 2/3 parentheses, 2/3 to 3, and 3 to infinity. You must pick a test value in each region. If it's not in the region, it doesn't do you any good. So less than negative 3, we could use negative 4. Since we changed signs here and we didn't use 0, we could use 0 in the middle there. Between 2/3 and 3, we could use 2. And bigger than 3, we can use 4. Once you've got your test values picked, I usually make a line, and then I put all of my factors over here on this column to kind of help me know what I'm plugging into. X plus 3, x minus 3, and the goal is that when we're done, we want it to be less than 0. Now this chart works as long as you have your factors on the left and your greater than or less than 0 on the right, because we read from left to right. So if we plug all of these in, this is a negative 12 minus 2, so that's going to be negative, and we only care about the sign. Negative 4 plus 3 is negative, negative 4 minus 3 is negative. 3 negatives multiply to make a negative. 3 times 0 is just going to be 0, so that's minus 2, so that'd be negative. 0 plus 3 is a positive 3. 0 minus 3 is a negative 3. 2 negatives multiplied together make a positive. 6 minus 2 is positive. 2 plus 3 is positive. 2 minus 3 is negative. 1 negative overall is negative. This would be 12 minus 2, so that's positive. 4 plus 3 is positive. 4 minus 3 is also positive, and that multiplies to a positive. We wanted less than 0, which means we want negatives, so we circle the regions that make that true statement, and then your intervals are up above. So this is negative infinity to negative 3, union with 2/3 to 3. So that is the true intervals, or the places where this original inequality would be true. All right, let's look at number 8. It says, given the points A is -3, 4, and B is 5, 6, find the following information. So we want the exact distance, which means we need our distance formula, which is really just the Pythagorean theorem in disguise. So a squared plus b squared equals c squared, but we've got it solved for c, so it's a square root right now. And if you need to, label your points, make yourself have an easy life. First ordered pair and second ordered pair. So this means that we would have the distance is equal to 5 minus -3 squared plus 6 minus 4 squared. So that's a minus a negative, so that's a plus, so that's going to be the square root of 8 squared plus 2 squared. You cannot take the square root of each of these yet because there's a plus between them. So this is 64 plus 4. So this is the square root of 68, which does multiply as a 4 times a 17. So this would be 2 on the square root of 17 if we reduce our radical. And that is exact. We don't want to use our calculator to come up with a decimal because it asks for the exact distance. This says write the equation of the line through AB and write our answer in slope intercept. So we need to find the slope, which means we need to do y2 minus y1 over x2 minus x1, change in y over change in x. That is 6 minus 4 over 5 minus -3. So that's again a plus plus there. So this is 2 over 8, which is 1/4. And then remember we have point slope formula that helps us find our equation. So y minus y1 equals m parentheses x minus x1. You just need one of your points and your slope. So I'm going to do y minus 6 equals m, which is 1/4, times x minus 5. You can distribute the 1/4 or you can multiply a 4 to the other side. That also clears that fraction out by just leaving the 1 on that side. So I just multiplied both sides by 4 to make that happen. That cleared out that fraction right there. And then I distribute this. This would be 4y minus 24 equals x minus 5. We're trying to solve it for slope intercept, which remember is y equals mx plus b. So we're going to add over our 24. So that would make that a positive 19. And then we'll divide everything by 4. I'm going to double check myself. Yeah, it's -5 plus 24. Yeah. And then divide everything by 4, and we get 1/4 x plus 19 over 4. And we don't worry about turning anything into decimals. All right, number 9 is the difference quotient. We are looking at using this formula to evaluate, essentially this is still slope in disguise, essentially, but we're calling it f of x is the y value for an x coordinate, and f of x plus h is the y value for an x coordinate that is h more than the original. So we just need to work out the f of x plus h and the negative f of x to put them in our numerator. I sometimes like to do this on the side. So we have everywhere there's an x, you're going to put an x plus h. Notice it's going into where x used to be, so it's getting squared. That is going to make it where you have to work out this squaring by writing it twice and then foiling. That is x squared plus xh plus xh would be plus 2xh's plus an h squared. We also need to distribute that 3 to everything in the parentheses. And then negative f of x just means change the signs of your original function. So that's -3x squared minus 7. So that's my numerator. So this would mean that the difference quotient here is equal to 3x squared plus 6xh plus 3h squared plus 7. I don't need to worry about the minus because I've already done that. Minus 3x squared minus 7 all over h. Now if we've done this correctly to our polynomial, we'll see cancellations of lots of things on top. So this is 6xh plus 3h squared over h. You can factor an h out of the top. Still have 1 on that 3. And reduce it. So my final answer is 6x plus 3h. And this is a big lead into something we do in calculus. So it's important to practice this if you're going on to calculus next. Okay, number 10 says determine the domain of the function and express our answer in interval notation. So when you're dealing with domain of a function, if you have a rational function, you want to make sure you don't divide by 0. If you have a radical function, you want to make sure the inside stays greater than or equal to 0. If it's in the denominator, it can only be greater than 0 because you don't want it to equal 0. We would divide by a 0 then. So I need to make sure that, and so down here we can't equal 0. So we need to make sure that 2x plus 30 stays greater than or equal to 0. That's one condition to keep that radical from being imaginary. So that means we have to keep x greater than or equal to negative 15. So you can already think about this as a number line that can never go below negative 15. And there's a bracket there. It's okay if it equals it, but it can't go below it. And then this we would factor and see if there are any numbers that would make us divide by 0. So factors of 28 that have a difference of 3 would be a positive 7 and a negative 4, because that multiplies to negative 28. So x cannot equal negative 7 or 4. You would then think about where those should be placed kind of on the number line. As long as they're on the right side, we need to make sure we omit them from this problem. So we're going to think about open circles, because those make us divide by 0. So if something falls over here on the left of negative 15, it's already been thrown out, so it doesn't really matter. So this is written as negative 15 to negative 7 with a parentheses on the negative 7, bracket on the negative 15, union negative 7 to 4, because it's anything in between here is also okay. And then this goes on forever, so union with 4 to infinity. So that is my domain. Okay, moving on to number 11. We're going to, for the following function, find its domain and sketch the graph. You can definitely do this by a table of values, but we've learned about transformations, so I'm going to show it that way. For a radical function, we've learned a couple times throughout this review that you have to keep this inside greater than or equal to 0. So there's my domain. So domain is that I have to use x's that are greater than or equal to 3. And then sketching the graph, this is just a transformation of a function. This is the parent graph. If our parent graph, let's call it g of x, is square root of x. We've learned that square root of x has a very specific shape. Square root of 0 is 0, square root of 1 is 1, and square root of 4 is 2. So notice this is what square root of x usually looks like. If you have a minus or plus something inside of your radical, that means you're going to be doing a horizontal shift. And we do opposite of what we think. So minus 3 is actually going to move us right 3. If you have a negative in front of your parent function, so that's the parent function, the square root symbol, then you're going to reflect over the x-axis. It's going to flip you upside down. And then if you have a plus or minus something after the function, that is a vertical shift, and you do exactly what you think. So this is down 4. So anything that happens inside the parent function is affecting your x values. Anything that's happening outside affects your y values, which is your, are you up or down? So if we look at this, the way you would graph these is you do the transformations as an order of operations. So essentially the things that are closest to x go first. So this is inside, it goes first. This is times, so it goes second. This is add or subtract, so it goes third. And we can just graph these one at a time and show that our final answer is the last picture. So if I move everything right 3, 0, 0 would move right 3. 1, 1 would move right 3. So 1, 1 goes 3 to the right. And 4, 2, which used to be right here, will also go 3 to the right. So 4, 2 goes 1, 2, 3. So that's my right 3. So that's stage 1. Stage 2, we're going to reflect over the x-axis, which means your y's will change signs. So we're right now at 3, 0, and that means your y is 0, so it can't change signs, so it's going to stay where it's at. This is 4, 1, so it'll be 4, negative 1. And this is, let's see, 5, 6, 7, 2, so it's going to be 7, negative 2. So notice now my graph is upside down. Excuse the pen strokes, it's kind of hard to draw on this. And then the last one is down 4. So this will be our final answer. This will be the transformation function. So f of x, which is going to be step 3 now. Make this a little higher down there. So let's see, 1, 2, 3, 4, 5, 6, 7. And if you want, you can write your ordered pairs down. Sometimes that helps people. Okay, so we were at 3, 0, and we have to go down 1, 2, 3, 4. So that's where 3, 0 has moved. We were at 4, negative 1. So now we have to go down 1, 2, 3, 4. Sorry, I'm not counting correctly. We're at 4, negative 1, and we go down 1, 2, 3, 4. So it's 1 below that one. And then we were at 7, negative 2. So we have to go down 1, 2, 3, 4. So our new graph has been shifted right 3, flipped upside down over the x-axis, and then down 4. So that's our final picture. For number 12, we're graphing a piecewise function. This is just a graph where we have the whole picture is chunked up in different domain functions. So we do a different function for different domains. So I like to think of this as doing just, and there are other ways to do this, but I like to think of doing however many rows I have, I do that many tables of values for each function. So I'm going to do XY charts for each of these. You can also think of these as kind of transformation of functions and just covering. Some people graph the whole function and then cover up the piece they don't need. I've seen these done a couple of different ways. The key to doing it with tables is that no matter if this is equal to or not, you must include each endpoint in your chart. -3, -2, -1. Now you don't have to do every point in between. I'm just doing that for emphasis on here. You want to make sure you have enough points to plot though. And this function is y equals 4, so no matter what x you plug in, it will always have a y value of 4 because there is no x in the function. Now I will make a note that this endpoint is closed because it has the equal to, and this endpoint is open. All the points in between are just regular points, but these are our endpoints. The next function is x squared, and we're supposed to go from -1 to 2. So -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And again, my endpoints, since there are 2 of them, this one is closed on the end and open on the end. And then my last one is from 2 to infinity. So we obviously aren't going to graph all of those, but we can maybe do 4 points. And the endpoint 2 is closed. It's hard to write. And then this guy is ... So that means we're going to have an arrow going towards the infinities. Okay, so if I put in here, this would be 4 minus 5, so that's a -1. 6 minus 5 is +1. 8 minus 5 is 3, and 10 minus 5 is 5. So once we have all of our information, we're going to graph it to the best of our ability. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll put 7, 8 on all of these. Okay, so at -6, we need to go up to +4 and put a closed circle. And then at -1, there's also an open circle at 4. And remember, everything in between is also at 4. So this is just a horizontal little line. At -1, 1, we have a closed circle. So notice this passes the vertical line test because we don't have 2 points vertically attached since that's open. 0, 0 is a point. 1, 1 is a point. 2, 4 is a point. So notice I am plotting all of these because these are, this is not a horizontal line, it's a parabola. So I want to see that curve change. And my open circles aren't wanting to stay for a minute. And then the last piece is 2, -1 is closed. And then we have 3, 1, 4, 3, 5, 5, and this is going up forever in that same pattern. And that is how you graph a piecewise function. Okay, for number 13, it says express the following function in vertex form. So a parentheses x minus h squared plus k, then graph the function. If you're in the standard form, you need to complete the square to make this happen. So what you need to do, if this is not a 1 in front, is to pull out a common factor for the x terms. So that would make that x squared minus 2x. We're going to leave a blank because we're going to complete the square. Minus 4. And usually when we complete the square, we put a blank on the other side as well. We're going to put it on the same side, and we're going to do what's called an inverse operation. So whatever we end up adding or subtracting because of this, we will do the opposite in that second blank to counterbalance. It'll be like we added 0. So to remember, to complete the square, you take half of the middle term, and then you square it, and then we put that number here. So this is going to be plus 1, but we really did 3 times 1 because there's a 3 out front, so we really added 3. So to counter that, we're going to minus 3 right here. Okay, so this then becomes something factorable. This is 3 parentheses x minus 1 squared, because it's always this number right when you cut it in half. And then this is minus 7. So that is my vertex form. The reason this is nice is you can pull the vertex out. It's opposite of the number in the parentheses and exactly the number at the end. So 1, negative 7 is my vertex. And really, if you're graphing a parabola, you really only need the vertex and a point on each side. So 1, negative 7 is here. I like to put a V for vertex. If you put in 0 into the original equation, that's always easier than using the vertex form. You'll see that this is 0 minus 4. So that is the ordered pair 0, negative 4. So I can plot that as well. And then because of symmetry, think about how this is spaced. This is over 1 from the vertex and down 1, 2, 3. If we go over 1 and then up to 3, there should be a matching point because of the symmetry of parabolas. You could find the x-intercepts if you want, but it didn't specifically say that you had to. Okay, let's look at number 14. This is given two functions. We want to subtract them, divide them, and then compose f with g. So the first thing, and then we're going to state the domain of each of those. So the first thing is, how do we do f minus g of x? You take the first function, f, minus the second function. And this goes back to stuff we learned in Unit 1. You just need to get a common denominator and then subtract. So we're going to need an x minus 5 for the first fraction because it's missing that. And we need an x plus 2 for the second fraction. And then when we distribute on top, this will be x squared minus 5x. Make sure you distribute your negative. This will be negative 4x squared minus 8x all over x minus 5, x plus 2. Combine like terms on top, we get negative 3x squared minus 13x over x minus 5, x plus 2. So that's f minus g of x. Now we want to talk about its domain. When you're adding, subtracting, or multiplying, you just need to use the combined domain issues that you had from the original two functions, their intersection per se. So what these both have in common is that we can't use negative 2 or 5. So x cannot be negative 2 or 5 for our domain. And that is true because that would make both of those divide by 0. Now next one we're doing is division. So this is a little more complicated with domain. So I always write it as a stacked fraction first with f of x over g of x here. Left out my x. Then we would normally just say let's multiply by the reciprocal of the bottom. And notice the x on top cancels with the x on the bottom here. So this becomes just x minus 5 over 4 times x plus 2. Now if you hadn't written your stacked fractions, you might just think your domain is just not negative 2. But it's anything that caused an issue in the original stacking. So we have this is a denominator, and this is a denominator, and this is also in the denominator. So pretty much because that 4x was in the denominator of the big fraction, we have to make sure we also throw out 0 with the negative 2 and the 5. So f over g of x is x minus 5 over 4 times x plus 2, and its domain issues are negative 2, 0, and 5. Okay, if we look at the last part of this one, we're doing f of g of x. And that means that we're composing the f function wherever we had an x. So this is that function, x over x plus 2, with the g function going inside each blank. So remember, this is a substitution. Now, we want to multiply everything on top by x minus 5 because that will clear out the fractions that are in there. So the top just becomes 4x, the bottom is a 4x, but then we have to distribute the 2 to both the x minus 5 parts. So 2x minus 10. So f of g of x is 4x over 6x minus 10. We could actually go another step with that and reduce it by 2. So that's 2x over 3x minus 5. And then this part right here is definitely my composition, but then my domain is the issue here. So when you're doing a composition, you have to make sure that whatever the inside function is, you respect its domain. So we can't have 5 because that makes those little fractions divide by 0. And then your new answer at the end could also have a restriction. 3x minus 5 equals 0 when x is 5/3. So our domain issue here is that we can't equal 5/3. So x cannot equal 5/3 or 5. And I am losing battery power and I don't have a plug-in, so I'm going to have to stop this video here. I will make a separate shorter video for the last 5 to 6 problems of the review.